It's the year 2126, and a million people call the moon home. While the sprawling architecture of Luna Prime looks like a triumph of human expansion, it remains the most hostile environment our species has ever occupied. Without an atmosphere to create drag, tiny micrometeorites travel faster than sniper bullets. A single rock moving 50 meters a second will easily puncture an oxygen tank or crack your helmet open. If you dodge the debris, an abrupt solar flare can still pass through the hull and shred your DNA to ribbons. Humanity subjected itself to these fatal conditions for a specific mathematical reason. To understand why we stay, you have to look at the physics of leaving. To see the logistical hurdle of space travel, look at this breakdown of a rocket launching from Earth. To reach escape velocity, an enormous 90% of the rocket's total weight must be dedicated entirely to fuel. Now compare that to a launch from the moon. Because you are working in only 16% of Earth's gravity, any launch from the lunar surface is 84% easier. You can move the same payload with a fraction of the propellant. This advantage makes the moon a mandatory waypoint. Luna Prime is the low-gravity gateway required to reach Mars and the rest of the solar system. Building that gateway required solving the moon's extreme geography. At the lunar equator, you face 14-day stretches of pure darkness, where the temperature plunges to minus 73 degrees Celsius, well beyond the limits of most terrestrial machinery. To solve the power and heat crisis, NASA placed the city on the Shackleton-Digger-Losh Ridge at the South Pole. Because of the moon's axial tilt, this high ground is bathed in near-constant sunlight, providing a continuous source of energy. The location offered a second critical resource. The deep craters adjacent to the ridge exist in permanent shadow, acting as cold traps that have preserved billions of years' worth of water ice. By selecting this specific geographical anomaly, engineers secured the two foundational requirements for survival: continuous solar power and a harvestable water supply. Even with water and power, early residents struggled with shelter. In the 2030s, crews lived in pressurized metal habitats, but abrasive lunar regolith destroyed the mechanical seals, leading to constant air leaks and decompression risks. Since shipping heavy steel from Earth is cost-prohibitive, engineers began harvesting the lunar dirt itself. Regolith is rich in silicon, iron, and aluminum, the raw ingredients for a high-strength lunar concrete. Construction relies on powder bed fusion. High-powered lasers sweep across the surface, which melts the powder into a molten state that recrystallizes into a structural ceramic. This process allowed for the 3D printing of massive, thick domes. This shielded architecture is the only scalable way to block both radiation and micrometeorites from reaching the population inside. Within those domes, the city must maintain a constant flow of electricity to power life support, oxygen generation, and artificial heat. A single computer glitch or power failure could cause the entire ecosystem to flatline. Maintaining that grid requires massive energy storage systems that can bridge fluctuations and handle the city's exploding demand. To build these batteries at scale, engineers rely on high-grade graphite. Graphite is used because it remains highly conductive and chemically stable even at extreme temperatures. This resilience allows the city's storage arrays to manage intense heat and deliver steady power in a harsh environment that would cause standard components to fail. This flawless power stability is what allows temperature-controlled hydroponics to work. It ensures that crops like rice and leafy greens have the consistent light and heat they need to grow in low gravity. Mastering these advanced materials is what allows raw solar energy to be transformed into the reliable life support that keeps the city alive. Even with the air and lights on, the human body is not built for the moon. Long-term exposure to 16% gravity causes severe muscle atrophy and bone density loss. To prevent physical degradation, engineers built massive spinning centrifuges inside the domes. In this schematic, you can see how the rotation pushes outward against the floor, artificially simulating the sensation of Earth's gravity. These habitats can be relatively compact. A centrifuge only 50 meters wide, spinning at 6 revolutions per minute, provides enough force to keep residents healthy. Beyond the physical toll, isolation presents a psychological threat. The Mars 500 project proved that living in tight and closed quarters for a year can lead to severe cabin fever and social withdrawal. Overcoming these biological and mental limits requires a combination of artificial gravity and expansive communal architecture, proving that we can engineer our way past our own physical evolution. Luna Prime has evolved into a fully realized metropolis. It is a self-sustaining, closed-loop system that recycles its own water and generates its own atmosphere. This achievement is built directly on the foundations laid by the early exploration missions that first surveyed this barren landscape. It also required a massive logistics chain, utilizing heavy rockets to haul the first generation of tools and materials out of Earth's gravity. By solving the constraints of air, water, and shelter on a frozen, irradiated rock, humanity has created a blueprint for survival that can be applied anywhere in the solar system. Establishing a permanent presence here transforms the Moon into a staging ground for Mars and the asteroid belt, opening the door to a multi-planetary future.